There we go. All right. Now, let's take a look at where we are. And okay. Now, um, we had uh, we had finished uh, this page last time, and uh, I don't think I had clicked on the checkpoint. Um, but now I will, and it will be officially for tomorrow. And now, again, you need to practice these very carefully because they're going to be really, really important that you're able to do the nomenclature. And these may or may not be what's on D2L. My recollection is that they are not exactly the same as what's on D2L. So use the file that's on D2L for checkpoint 2 number 5 and put it in the checkpoint 2 number 5 Dropbox in D2L. Okay. Now, we're trying to build some intuition in chemistry to sort of understand how reactions take place. And we can use the periodic table to predict some reactions maybe that we haven't seen before if we know some other ones. For example, here's a reaction of hydrochloric acid with calcium carbonate. Um, it would form calcium chloride water and carbon dioxide. And that is a very well-known reaction. Calcium carbonate is limestone. HCl is called by industrialists muriatic acid. It's used to wash bricks and things like that when they put mortar on and get a little bit on the brick. They can wash it with this, quote, muriatic acid, which we all know is hydrochloric acid, and it will wash off that mortar that's containing calcium carbonate. And so you won't see that reaction perhaps unless you're a carpenter or a builder. Okay, but this reaction is known to occur. We can look in the periodic table and suppose I'm looking at this reaction, hydroiodic acid and barium carbonate. Well, maybe I've never seen either one of those. And I don't know the reaction. What I would go to I would go to the periodic table and I'd locate iodine, and then I would look in that column and just above it, I'd see chlorine. So I know HI is going to react the same way that HCl does. And similarly, I would look for barium, and barium is in group 2A, and calcium is also. So I would say, okay, barium will do the same thing calcium does. So all I've got to do is just replace calcium over here and barium. I can replace the chlorine here with iodine and get a similar reaction. And I can replace the calcium with barium. And then I predict the products of the reaction. So if you know one reaction, you can go to the periodic table. Anything in the same family will behave the same way. It may not be as fast, and in some cases, it might not even really happen. But you know, we're not learning specific details. I'm not Google. What we're going to do is we're going to learn principles and apply those principles. And often we'll get answers that if you go to Google, would predict something different. But we're going to go for what is expected. Now, if you do reactions with oxygen, they're often called combustion reactions because you also see a flame. But what happens in a oxidation reaction? Oxygen reacts with almost everything on the periodic table. And what you will make in a reaction with oxygen is the oxide of every element that's shown in the reaction. So you'll make NO2. That's the most likely oxide. You could make one of the other oxides of nitrogen. And but this one is the most likely one. It's one of the most stable ones. You could make NO, for example, but not in the presence of oxygen. Immediately, NO would react with oxygen to make NO2. You could maybe make some of the higher oxides, and they might or may not be stable. But if you got any of them at all in this reaction, they would be minuscule compared to the amount of NO2 that you get. Again, that will come from experience. The oxide of hydrogen is water, of course. The oxide of carbon is carbon dioxide. That's the most likely one that will happen. You could make carbon monoxide. We hope you wouldn't, but that would be very poisonous and dangerous, but it's possible, but not if you've got enough oxygen around. Oxygen will react with carbon monoxide to make carbon dioxide as well. Sulfur dioxide is the most likely product. There is also known an SO and an SO2, SO3, I'm sorry, but SO would react with oxygen to make SO2, and SO3 is not likely to form directly without a catalyst. You don't know that? I would accept either one of them. But here's the expected oxide. And then if you balanced it, this is the numbers you'll get. We'll get to balancing equations very, very shortly. Okay, now, if you've got a reaction that's characterized by only one product, then that's going to be what we call a combination reaction. And you can make that, you could imagine, and you would be able to take calcium oxide and sulfur trioxide. They would react together to make calcium sulfate. This reaction certainly would occur very quickly. There are some other reactions that you could predict. You could say, okay, well, maybe the elements would come together to make SO, calcium sulfate. But you've got to remember, reactions occur by actual physical contact between the elements. So if we took solid calcium and solid sulfur and oxygen, and you have a question? Okay, if you take these, they would bump into each other and there would not be one speck of this compound formed. Now we can imagine that reaction forming, but it actually will not happen because instead you get all of these reactions with oxygen is much more reactive toward these elements than it would be in a combination reaction like that. So what you would get instead of the calcium sulfate, you would get SO2, calcium sulfide, and calcium oxide. These are the compounds that would actually form. Now, how would you know? Well, again, that would come from experience. And let me make a point here that's going to be important, really, really important later. It doesn't really matter how you make that if you got it. You know, I got it. I don't care how it came from or how it got to be there. One of the ways you can imagine that it got to be there, although that isn't what happened, is this first reaction with the elements. That's called a formation reaction. They are really seldom possible. But you know what? We can pretend they do happen, and we're going to be able to put these together in some very important ways, just imagining that everything we see in the reaction was actually formed from its elements. Remember, if you've got calcium sulfate in a bottle, you don't care, you don't know or even care where it came from. You just know you get some calcium sulfate out of that bottle. That's the way reality is, and we can then imagine ways at getting to that reality. Doesn't mean they happen, but it happens as if they had. It would be just the same outcome. Okay. Now, if you have a reaction that has only one reactant, that's going to be a decomposition reaction. And of course, if you take good old Tennessee limestone and you heat it up, you'll make calcium oxide and carbon dioxide. This is a very common reaction. That is the reason why if you put stones around a fire pit and come back the next day after you had the rip-roaring bonfire, the stones are sometimes cracked and and kind of look funny, like it's kind of a grayish, different color and texture on the surface. Well, the reason for that is this reaction took place and destroyed some of the calcium carbonate at the high temperature. And it takes a pretty high temperature to do that. I think it's somewhere close to 800 degrees Celsius. So it's really has to get hot to do that. But you can actually make these gases that way, and the calcium oxide solid. Now you could imagine that if you heated it up, oh, you might get the elements again. Well, no, you're not going to take calcium in the presence of oxygen and have that form together. They'll react with each other to make calcium oxide. And the carbon in the presence of oxygen is not going to react with, are going to react with each other to make the carbon dioxide. So the decomposition is not going to make the elements because they would react with each other. But we can imagine that they did if we want to. What would happen instead is the calcium and the carbon would make calcium carbide. You may have heard of it. It's a chemical that they used to use in headlamps for miners. Had a little calcium carbide in it. If you put a little water on it, it makes acetylene, just like in the acetylene torch. And that gas sprays out through a little opening that you can ignite and have a reflector behind it to make a little headlamp. And miners use those carbide lamps. But calcium and oxygen would just make calcium oxide. So these are actually the products you're going to get. But the important point again is you can decompose that. And if you want to imagine that it went to the elements for some reason or other, hey, it's okay. It's one of the possible things that could potentially happen. In reality, it doesn't, but we don't really care. We just know that we're going to decompose this stuff. That's what's important to us in some cases. Okay, now, here's some problems with the law of multiple proportions and so forth. I'll go over that a little, but you've already had an experiment on that, and so I'm going to go very quickly. I'm going to skip this part about Dalton's theory and just go directly to the multiple proportions part. Now, what I'm doing in this reaction is I'm going to make sure the law says I have to have the same amount of one of the elements. In your checkpoint, I'd already done that for you. I gave you an amount that had 1 gram. So what I'm going to do is if I imagine for this first compound, and I want a 1 right there for the mass of sulfur, the way I could get that is divide that by 17.14. And that would give me 1 gram of this. Well, how much of the fluorine would I have? Well, I had a total sample that was 26.4. I had 17.14 grams of sulfur in it, which means the difference would be the amount of fluorine. So if I took the 78.2 and subtracted off 17.14, that's the amount of fluorine that's present. Then if I need to divide that by the 17.14, because that's what I did to the sulfur, and when I do that, I come up with 1 gram of the compound combined with 3.56 grams of fluorine. If I take the second element, compound B, and do the same thing to it, its sample weight was 26.4. It had 12.07 grams of sulfur. So if I wanted to have a 1 instead of 12.07, I would divide by 12.07. And that would give me 1 gram of sulfur. The amount of fluorine, as we did up there, would be the sample weight minus the amount of sulfur that was there. And then I want to divide it by the 12.107, like I did up here, to get the mass of fluorine. So in this case, 1 gram of sulfur would be combined with 1.19 grams of fluorine. For compound C, I would have it like this, and I would get this. So I can see that I've got 1 gram of sulfur in all 3 samples. This is the amount of fluorine in the 3 samples. the law says these numbers should divide to be whole number ratios. So if I go through and divide all of them by 1.19, if I divide 1.19 into 3.56, I get exactly 3. If I divide 1.19 by itself, I get a 1. If I divide 2.38 by 1.19, I get a 2. So these are in the ratio of 3 to 1 to 2, which is consistent with the law of multiple proportions. Now, here's, if the molecular formula of compound B is SF2, what is the empirical formula of A and C? Well, the ratio are 3 to 1 to 2. So that means that A has to be SF6. So for every, there's 3 times as much fluorine in the compound as there was in B. 3 times 2 would be 6. And if I look at compound C, it's SF4. So these are 3 known fluorides of sulfur. They can all be made in the lab, and they do satisfy the law of multiple proportions. And then if you look at the periodic table, you can get information. We get the symbol, we get atomic number, we get atomic mass, we get the physical state, and we get the class of the element from the periodic table. So nuclide symbols, we've got these. You know, I think I'm going to skip this because we really need the time. We've had checkpoints on all of this. So let's escape out of this one. And I'm going to go on and pick up the next PowerPoint. Okay, so let's go to here, back over to here. Let's go to here and go to, yes, let's go to segment 3. Okay, and now I need to share that screen with you to begin now segment 3. Now, whenever we write a chemical reaction or talk about chemical reactions, we use equations, and an equation is just some formulas put together with signs and then a group, and then generally an arrow. And the things to the left of that arrow is the collection of reactants. The things on the right are the things we call products. And we read the reaction, R1 plus R2 plus R3 reacts to form P1 plus P2 plus P3. Here's a word equation for a reaction that takes place. Sodium hydroxide and sulfuric acid form sodium sulfate and water. The correct formula for sodium hydroxide, you should be able to already know this answer if you memorize hydroxide, because the element name on the left is the same as the element. The symbol for sodium is Na. The thing on the right-hand part of the formula, a name, is the anion part, and hydroxide is OH minus 1. So Na plus with OH minus 1 would give you NaOH as the correct formula. Sulfuric acid, it doesn't have hydro, so it means that it's the hydrogen compound of sulfate ion, and sulfate is SO4 2 minus, so I need 2 hydrogens in the compound. And then I would say, okay, it forms sodium sulfate. Correct formula is Na2SO4. Sulfate is minus 2, so I'm going to need 2 sodium plus 1 ions to balance charge. And water is the other product. It's not balanced, but I'd have to go back and balance it later, and we'll worry about that in a moment. Now, I want to also help you with interpreting formulas. We've done everything except this 2 out front already in some checkpoints. And now, I want you to look at how we get the number of atoms of each element. This 2 multiplies everything that follows it. The whole formula is doubled because of that coefficient in front. There are 2 aluminums in each one of these units. And there are then a total of 4 aluminum atoms. So it's 2 times 2 to give me the aluminum formulas. If I want to do sulfur, sulfur is inside sulfate. There's 1 sulfur in sulfate, but there's 3 of them. So it's 3 times 2 is 6 sulfur atoms. And then if I want the oxygen, it's 2 times everything. We have 3 sulfates, and each sulfate has 4. So it's 3 times 4 times 2 is 24. So you have to be able to do this to do our next exercise on balancing equations. And I just wanted to reemphasize how you handle the 2. This 2 multiplies everything. That 2 only multiplies aluminum. That 3 multiplies everything in that parenthesis. And that 4 only multiplies the oxygen. So oxygen is 4 of these. Each one has 3 of these. Each one has 4 oxygens. And there's a total of 2 times the whole thing. So that's how you figure out the number of atoms represented by something in the formula. Now, the law of conservation of mass would be obtained if we can guarantee that happens if we count up all of the atoms. We want to make sure we've got the same number and same kind of atoms on each side of that arrow. That's what we mean by balancing an equation, is making it conform to the law of conservation of mass, so that the mass of the reactants will always equal the mass of the products. Remember, in Dalton's atomic theory, the atoms of the reactants just change partners to become the products. So the total number of atoms of each kind is the same on both sides of that arrow. And that's what we do to do that, to balance the equation. Now, let's look. Here's your checkpoint on this one, which is also due tomorrow. And it's similar to that. It may or may not be the one that's on PowerPoint on D2L. So be sure that you do that one as you do this checkpoint. Now, I want to ask you to do something for me. Just imagine you never had chemistry before, because all of you, if you've had chemistry before, you balanced equations by what they called inspection usually, which means that you just tried some numbers until they worked. We're going to get examples that are way too hard for that. I balanced one equation. I think that the largest whole number coefficient in the balanced equation, I think it was 1837. Yes, I said 1837. Do you think you could ever in your lifetime just guess numbers until you come up with that number? I don't think so. So I'm going to show you a method that always works and leads to the correct answer in the least amount of time. Believe me, I'm going to give you examples on the quiz that if you don't do them this way, if you do that balance equation problem first, that's probably the only one you'll get done on the whole test. So please pay attention now. I'm going to show you something you haven't learned before, I don't think. And it's based on some work that I did when I was working for NASA one summer. I'd been, I'm a teacher, so I'm a teacher everywhere I go. And so I'm thinking about balancing equations for teaching my students. And I came to an idea because of what I noticed. If I start balancing an equation, let's say it had 5 elements in it, and I start balancing it. I balance the first one, and then I balance the second one, and then I balance the third one. Then I balance the fourth one, and lo and behold, the fifth one is already balanced. So to me, that meant there's something fundamental about that law of conservation of mass that's keeping the same amount of elements on each side of that equation. And what my postulate was, or my hypothesis was, that there's really only two variables in an equation. And when you specify one of those variables, it'll predict the value of the other one. So let me go through the method. I tried it and it worked. Um, I found, in fact, one of the reactions that I used is on this. It's got some pretty unique coefficients as well. But what I did is I went, while I was working for NASA, maybe, no, I think this was at Redstone Arsenal. While I was working for them, I'd have some stuff going on in the lab that didn't need my attention. So I would run over to the library, which is the same building, and I would look up some things that I was researching. And one of them was to find if my hypothesis was correct or not. So I looked up some articles about balancing equations and ran across one that I thought was, that one was made for me. It said the title of the paper was 5 Impossible Equations to Balance. So I said, okay, we'll see. So I took wrote those 5 equations down out of the paper, and I copied down all of his references for later work. And I went home that night, and I decided I'd go ahead and try my theory, my hypothesis on that set of equations. And the first couple of 3 dropped right out in my lap. They did exactly what I thought. I had them balanced in seconds and no problem at all. I went to the next one though, and when I got to the end, it didn't balance. And so I thought, oh my goodness, my theory is not right. And so I then took the references that I had copied down and looked up that paper in its original reference. And the reaction involved sodium and sulfur and oxygen as some of the elements, but he had left off sodium sulfate as one of the products when he wrote his paper on the impossible reactions. Well, his was impossible. And so when I put in the sodium sulfate from the original paper, it again dropped out. So this method, I've tried very hard to get this published and sent it to the publisher many times and got rejected, but because they said they had published enough on balancing equations. They weren't going to publish anything else on that. Okay, so it's not been published. Here's a reaction, though, that I can use to illustrate the method with you. So well, this one you could probably balance by inspection pretty easily. But if you'll be honest with me, I think you'll see the method I'm going to show you actually works quicker, and even with a simple equation like this one. Now, you need to know where to start and what to do next. That's the important thing in balancing the equation. Don't just try stuff. Do something that will change that equation, and then do something that you just changed as the next thing you do. So we're going to begin with the reactant that it has to appear in only one reactant. The element has to appear in only one of the reactants and one of the products. Well, carbon does, and hydrogen does. Oxygen's in several places, so we wouldn't pick oxygen, but we could pick either carbon or hydrogen. And what I would like to do is pick the one that has the most atoms showing. Well, there's 6 carbons and 6 hydrogens, so it wouldn't matter. I could start with either one. The other one would be the next thing that I would want to do. And so now, if I'm going to balance this equation by the inspection method you talked about, and I was trying to balance carbon, I would put a 1 right here and a 6 right there, right? We're going to do the same thing, except instead of putting 1 and 6, I'm going to put 1A and 6A. Okay, so I'm using a as a variable. Remember, I said we could have two. So that's going to be one of them. B is going to be the other one. Okay. So now once I put a right there, I would check off a balanced carbon and I would put a little dot over hydrogen. So I'm going to check off the one I balanced and dot the ones that are adjacent to it. And you'll see why in just a minute. So let's do this on this real reaction. Here it is. So I put an A here and a 6A there. That means I check off the carbon here and check off the carbon here. I put a dot here and a dot here. Now, this is now where to start. What to do next has to do with the dotted elements. Or remember back here, we had two choices. We could do the carbon or hydrogen. Well, I could balance hydrogen next, and it happens to be one of the dotted ones. So that's okay. We wouldn't want to do oxygen because oxygen, to balance it, I know there's 12A total, but I don't know how many more I have to add to this to get a number that goes here. So I can't do oxygen now. So I balance a different element in the same formula. So in other words, I'm going to one of these dotted elements and balancing it next. Okay, so I chose hydrogen as the next one. So balancing hydrogen, I had 6A hydrogens. I need a 3A here times 2 gives me 6A. That checks off hydrogen and dots oxygen. Now, at this stage, the only thing that's dotted is oxygen, and that's the only thing left. If I had a coefficient right here, this equation would be balanced. I've got another variable available to me. I said I could have A and B. So I'm going to balance oxygen. That last one, I'm going to balance it by putting a B in front of the oxygen. Now, I'm looking at that equation. I've got a coefficient here. I've got a coefficient here. I've got a coefficient here and one here. Every element, every formula in the whole equation has a coefficient. It is balanced. That's what we mean by balancing, is getting coefficients in front of each of the substances in the reaction. So now let's see if oxygen is in fact balanced. Okay, so the number of oxygens that I have on the left is 2B. The number of oxygens I have on the right is 2 times 6A is 12A, and 1 times 3A is 3A. So 2B has to equal to 15A. Now, that means these both have to be equal to the same number, and it has to be a number that both 2 and 15 will divide into evenly, because we want whole number coefficients. Well, what's the smallest number that both 2 and 15 will divide into? It would be 30. Okay, so there's 30 on the left and 30 on the right. So 2B equals 30. So that means that B is 15. And 15A has to equal 30. That means A has to equal 2. Now I do have, in fact, real numbers that I can go back up there and plug in and balance the equation. So 2 times A is 2. So I put a 2 there where A was. I'm going to put a 15 where B was. And then I'm going to take 6 times the value of A was 2, that's 12. And 3 times the value of A is 6. So this is the final balanced equation. You could go through and double check and be sure. There's 2 times 6 is 12 carbons, 1 times 12 is 12. 2 times 6 is 12 hydrogens, 6 times 2 is 12 hydrogens. 15 times 2 is 30 oxygens. I've got 24 from here, and 6 from here makes 30. It is balanced. Okay? Now, this one would take you a little more time if you did it by hand. If we made that NO2, it would balance pretty easily by inspection. This one is a little bit more difficult. In fact, in Gen Chem 2, we teach you a different way of balancing equations That's especially for reactions like this that we call redox or oxidation reduction reactions. But let's do it by the method that we started. Now, let's think where we're going to start. We want an atom that is not balanced as with just ones in there. Well, copper would automatically balance if I put a 1 here and here. So copper is not a starting place. Hydrogen, there's one hydrogen atom here, and hydrogen is only in this one. So hydrogen is a possibility of a start element. Nitrogen, well, there's nitrogen here and nitrogen here. Nitrogen is not. It has to appear in only one formula on each side, and certainly oxygen is not. There's oxygen in this one, and this one, and this one. So the only choice we have to start with is hydrogen. It's kind of a trivial, simple one, but we'll balance hydrogen by putting a 2A here and an A here. Then I've got 2A hydrogens on this side, 2A hydrogens on this side. I check off the hydrogen. I dot the nitrogen and the oxygen on the left and the oxygen on the right. My dotted elements are nitrogen and oxygen, and I can do neither because you see, I'd need a coefficient here and here to balance nitrogen, and I'd need a coefficient here and here to balance oxygen. We can only put in one coefficient at a time. Now what do? Students always ask me, how do I know when to switch from the A variable to the B variable? The answer is really simple. When you can't balance anything else with A, and I can't balance anything else with A here. So that means I've got to switch to B and switch to another element. None of the dotted ones. The only one left is copper. And so I'm going to balance copper next. And I just explained why. So let me reproduce what I've got. And I need a B in front of the copper to balance copper on both sides. 1B copper and 1B copper over here. Now, copper is balanced. And now, I've got one coefficient left. And it's going to be involved in this reaction as well. So here's what I'm going to do here. It's a little trick. I'm going to put an X there and then figure out what it is in terms of A and B. So if I do that, I'm saying, okay, now let's make one of those elements balance. And if I balance nitrogen, look on the left, I've got 1 times A is 2A. On the right, I've got 2 times 1 times B is 2B, and 1 times X is X. So I can solve this for X. I just need to subtract 2B from both sides, and I would get X is A minus 2B. So now I'm going to put that back into the place of the X. I just did this as a placeholder because I want only A's and B's to show up in the balanced equation. So this is now my equation. It has a coefficient in A and B in front of every formula. It is balanced. Okay, now the only element that we haven't balanced formally is oxygen. When I put the 2A minus 2B here, that balanced nitrogen. So I haven't balanced oxygen. It's the last element that's left, and I do have coefficients. Let's put the oxygen that's on the left is 3 times 2A is 6A, and on the right I've got oxygen here, here, and here. So I'm going to have 2 times 3 times B is going to be 6B. I'm going to have 1 times A is A, and 1 times 2A minus 2B is 2A minus 2B. I'm just going to collect terms, and when you do that, the 2A and I had 6A here, so I'm going to subtract 6A plus 2A more is 3A. So I'm going to subtract the 3A from both sides to put the A's on the left. So 3A from 6A leaves 3A on the left. Now my A's are gone. What I've got is 6B minus 2B is 4B. So this now gives the relationship between A and B. And I want to show you, we've got to again say, okay, the total number of atoms is a number that can be divided evenly by both 3 and 4, and that would be 12. But let me show you a quick and dirty way. The coefficient that is in front of the B is the value of A. And the coefficient that's in front of the A is the value of B. That'll always work. So A is going to be 4 and B is going to be 3. So now I've got numbers to go in and replace those variables A and B upstairs. So B was 3. So replacing the B with a 3 and replacing the A with a 4, that becomes an 8. Replacing the B with a 3 and replacing the A with a 4. And then A is 4, so 4 times 2 is 8, B is 3, 3 times 2 is 6, 8 minus 6 is 2. So the coefficient in front of NO is 2. So 3, 8, 3, 4, 2 is the balanced equation. Okay? All right. Now, there are other examples that you can follow in the text and practice on them. I'm thinking maybe I'll do one. I'm going to do this one with you. To do that, I need to switch over. So I need to stop the share here, and I need to change the camera. You don't get to look at my smiley face anymore. Okay, we go for you. All right. Now, it would help if okay, now you can see that, and I can see the equation I'm trying to balance. I've got HiO3 plus FeI2 plus H. Oh, you can't read that. I'm sorry. I forget this camera's got rotten resolution. I've got a new one coming in today. Maybe it'll be a little bit better, I hope. HiO3 and FeI2 and HCl goes to FeCl3 and ICl and water. Okay, I'm about to run out of space, but okay, I think we can do it. Now, I want to look at this and I want to say, okay, could I start with hydrogen? Well, there's a hydrogen here and a hydrogen here and only hydrogen here, but there's one here and 2 there, so I don't think I would want to do that. Well, could I do iodine? Well, there's iodine in 2 formulas on the left. That automatically rejects it. What about oxygen? Oxygen only appears in this one formula on the left and in water on the right. So oxygen is a possibility. So what I'm going to do is put a little dot over it just to remember things. Now, iron, could I do iron? Well, it is already balanced, so I'm not going to do it, but it would be a choice, just like the hydrogen would have been, except it's in 2 places. I still have rejected it. Now, iodine is in this formula and this one. That rejects it. Hydrogen, I've already talked about. Chlorine, could I do chlorine? No, chlorine's in 2 formulas on the left. So the only possible choices really are oxygen or iron. Now, what did I tell you? In those cases, you pick the one with the most atoms. So what I'm going to do is I'm going to pick oxygen to balance. And if I had an A right here, then over here for water, I need a 3A. Now that will balance oxygen. Now what was I to do next? I was to put a dot over the elements that were checked off. That becomes my next choice. And so I want to see, can I balance hydrogen next? Well, I need to know how many hydrogens that would go right there, and then I would have it. So there's just one formula that involves hydrogen, it can be done. Okay, how many hydrogens have I got on the right? 3 times 2 is 6A. I've got 1A here. How many more do I need? That's right, I need 5A. So for the HCl, I'm going to write 5A in front of it. And now that balances the hydrogen. Okay, now we will dot the chlorine because I put a 5 right there. And now I'm still looking at the elements to see if I can make them balance. Well, iodine, to balance it, I'd have to put in 2 coefficients, so I'm not going to try that right now. What about chlorine? Well, chlorine, if I don't know that coefficient or that one. Okay, now what do? I can't balance anything else that's dotted with the A variable. So what do? I switch to B and balance the dotted elements that's left. I still can't balance iodine because it's in 2 different places. So I have to do the iron. And I'm going to put a B right there in front of the iron, B, there. And I'm going to put a B, FeCl3 right there. And now that balances iron. We got iron balanced. It dots iodine, and it dots chlorine. So I've still got iodine and chlorine left. Now I can do the iodine. Iodine is just one place on the right, so I want the same number of iodines on the right that is showing already on the left. I've got A of them from HiO3, and I've got 2B of it on FeI2. So that means the coefficient in front of the ICl, I'm sorry, I should have turned this and did landscape. But okay. Now, the coefficient I need is A plus 2B. Okay, so I'm going to pull this out and copy it so that you can see it a little better. So I'll set this over here where I can see it, and let's free copy everything to make it look a little bit better. Pages up from underneath there too while I'm at it. Okay, so let's see what we've got. And I guess what we did was we balanced iodine, and I should put a dot over chlorine again. We balanced iodine. Now, so here's what I'm going to say. I've got AHIO3, all 3 have checked at this stage, plus B, FeI2, both of those are checked, plus HCl, I've not done anything with it yet. And now I'm going to, oh, yes I do, I've got 5A of them, 5A, and that's checked and that's dotted. And now over here I've got B, FeCl3s. I've checked the Fe and dotted the chlorine. And ICl, I've got A plus 2B. ICl, I is checked, Cl is dotted, plus 3A H2O. Oxygen is checked, and hydrogen should be checked, yes. Okay, now, so that's what we've got. And now, The only thing I see that isn't dotted is, I mean, that's still dotted and not checked is chlorine. But look, I've got a coefficient here, I've got a coefficient here, a coefficient here, coefficient here, coefficient here, coefficient here. The equation is balanced. I've just got to make chlorine balance. Okay, now, how many chlorines do I have on the left? Okay, on the left, I've got 3A chlorines. And how many do I have on the right? I've got 3B from here. I've got 1 times A plus, was that a plus? Yes, it was. Yes. Plus, I've got A plus 2B. And that's it, isn't it? Chlorine is just in this formula and this formula. Chlorine is just in this formula. So 3A equals 3B plus 2B. So if I subtract A from each side, I'll get 2A over here. I'll get 3B plus 2B is 5B over here. So A is going to be equal to 5, and B is going to be equal to 2. So now let's go back up here. This coefficient is a 5, so I want 5 HiO3. Now, B is 2, and so I want 2 FeI2, and HCl 3 times A is 15 HCl, and B is 2 FeCl3. And now A plus 2B, A is 5 and 2B is 4. Let's see, Daisy. I'm getting a number that looks funny to me. Okay, but let me see. A plus 2B, so that would be 9. I think I made a mistake somewhere. We'll check it and see. Probably messed up with all of that compression I did upstairs. And 3 times 5 is 15 waters. Okay, well, let's just see. I'm pretty sure I'm wrong, so let's see if that's going to be right. I can see right away that it isn't. 5 hydrogens and 15 hydrogens is 20, but I've got 30 on that side. Okay, and that means we need to back up and punt. And
for your hydrochloride on the reactant side, I think it was a 5A, not a 3A.
Oh, thank you. I couldn't read my own handwriting. Where is that? Oh, you're right. It certainly was. Okay. And so that's going to change all of this. So let's see. For chlorine balance, that would be a 5A right there. And I'm guessing everything else is okay. 3B and A plus 2B. Yes. And then that would give me, that would be a 4 then, wouldn't it? Subtracting 1A from 5 gives 4. And so that means A is 5, but B is 4 now. Okay, now let's go back and see what we get with these coefficients. Now, okay, all right, so we had A was 5, so the 5 was okay here. Fe was B, so this becomes a 4 instead of a 2. And 5 HCl's, so 5A would be a 25. And iron is B, which is 4. And now I got A, which is 5, and 2B, 8. 5 and 8 is 13. And 3 times 5 is 15. Okay, that's right. Okay, now let's double check and see if we're right. I've got 5 hydrogens and 25 hydrogens. For hydrogen, I've got 30 on the left, and I've got 2 times 5 is 30 on the right. Iodine. On the left, I've got 5 from here and 8. I've got 13 on the left, and 13 times 1, I've got 13 on the right. Oxygen, I've got oxygen's only in this one, so I've got 15 on this side. Oxygen over there, I've got 15 on that side. So all 3 of these are balancing. I've got an iron. On the left, I've got 4 from here and 4 from here, so they're both 4s. That balances. And chlorine is the only one I'm not accounting for. Chlorine. I've got 25 on the left. I've got 12 and 13 is 25 on the right. That balances. Okay. All righty. Now, that's the technique. And you really need to do some practice. And on D2L, I do have a file in content that says for this unit, Exam 1 materials, I've got a file up there that says practice equations to balance or something like that. And I want to tell you that there's a lot of them on there. There's just gobs and gobs of them. And I've used the periodic table to make some similarity reactions that really wasn't the ones we've done. But many of those equations, the parent ones, came from old exams and old quizzes. So you can see from that the level of the equations that I'm asking you to know how to balance. It's like the one down there that we've just done. And by the way, that was one of those 5 impossible equations to balance. And it is difficult to balance by trial and error. And I know you may have tried some other methods, but now here's the thing. On checkpoints for this, I will not give you credit if you don't do the method I showed you. I want to force you at least one time to do it, and then it's okay to make a choice. If you can look at that and say, you know what, I don't need to do it that way. I can do it another way. When we actually go to exams and quizzes, all I'm going to know is whether you got the right answer or not. And I don't know how you got it. I really wish you would use the methods I show you. But if you come to a good, logical reason why you don't want to, that's okay. But I want to know that at least once you did it the way I showed you. So you had some data to base your decision on rather than what was comfortable. We're going to do a lot of things that aren't totally comfortable. It wasn't comfortable to me to do all that grading this weekend. Okay. All right. Now, this is the checkpoint or one like this. And so this is another balance equation. I'll go through the same things that we've done. Okay. So sometimes when you go through equations, especially when you have to put in a 2B instead of we did an A and a B right here, but when I got ready to balance with one of those atoms, I guess it must have been the hydrogen. Yes, you can see from hydrogen right there with a 2. So no matter what coefficients you get, the number of hydrogens is going to be an even number, not an odd number. So the only way you can guarantee hydrogen will be even, now this part's going to always be even, 4 times 1, 2, 3, 4, 5, whatever number is going to be an even number, but this one could be odd. So in order to make that not the case, so that you couldn't, there's going to be an even, I went through and doubled everything right there when I did the balancing, because I anticipated that problem there. Now, sometimes you won't know that until you get to start to calculate a coefficient and it comes out a fraction. If it comes out like 1/2 or 3/2 or something like that, or 1/3 or 2/3, whatever's in the denominator for that fractional coefficient, you need to go back and double everything and go through again. When you get done, you'll get this. This is a balanced equation. That's not the way I want you to report it. See, you see all the numbers now are even numbers, so that means a 2 can be divided out of all of them. So you divide them by 2 and you get, this is the coefficient I'd want you to show as the answer.
Dr. Pearson?
Yes.
We are just still looking at the equation we just balanced. We're not seeing what you're looking at on the screen.
Oh, thank you.
You're welcome.
I need that reminder every now and then because sometimes I forget. Okay. This is what I was looking at, and this is the reaction that I was doing. It's segment 3, checkpoint 2 example. I just did another balancing equation with copper and nitric acid. This is a methane and nitric acid. This is one of the equations on that list of possible equations to balance for practice. And what I was noting that if I started out with an A and a B here, I would see that I'd have a problem with hydrogen. Hydrogen's going to always be an even number. The only way I can guarantee that the hydrogens on the left will be an even number, whatever put here, methane, 4 times that's going to be an even number. But if this is odd number, the number of hydrogens on the left will be odd, and the number of hydrogens on the right is always even. So I'm going to double both of these coefficients before I start to balance. And when you do that, very often when you get to the end and get the equation balanced, it's still got that factor of 2 in it. And so if you get a coefficient that comes out somewhere in the balancing process, it's going to be a fractional coefficient. Go back and multiply by the denominator and come back to that stage. When you balance that element, then it'll work with a whole number. But often you'll come out with an equation that can be reduced further. I want you to always report the lowest set of coefficients, smallest set of coefficients that balance the equation. So here's the one you to do. It's also one of the equations that's on that practice sheet. And the one on segment 3, checkpoint 2, might be on the same that's on that checkpoint on D2L, but it might not be. So again, what I want you to do is take the equation that you get, and in this case, I'm guessing that the equation on the, no, I put them all in Excel format, I think. But anyhow, whatever format it's in on D2L for checkpoint 3, number 2, be sure you work it out in that same file type, either Word or Excel, and drop your answer into Dropbox, segment 3, number 2. It's not up yet, I think, but I will put it up this afternoon. Okay, so there's your checkpoint on that. Okay, now, let's continue. Okay, all right, there you go. And righty, and now, let's look at the elements and their characteristics. Metallic elements, and reminding you, I don't want to break and pull the periodic table up, but if you look at your periodic table, over on the right-hand side, there are some bolded steps. It's boron and aluminum, silicon and gallium, arsenic and antimony, tellurium and polonium, and astatine form a little zigzag step pattern. That is the dividing line between the metals that's on the left of that and below, and the non-metals that's on the right and above. Characteristics of metals are that they're shiny, they have a mirror-like reflectance. Now, that just means that all the light that hits the metal gets reflected, but it's more than that. If, for example, you look at a piece of white paper, all the light that's striking it is also reflected. So what's the difference between the metallic substances that give a mirror-like appearance and the paper substance that's just white? They both are reflecting all the light that hits them. What's the difference? Well, here's the difference. Whenever light interacts with matter, it's got an electric and a magnetic field. The electric field, as it vibrates, influences the position of the electrons. In one part of the wave, when it's going past the metal atom, the electrons are pushed in one direction, and in the next half of that wave comes by, it's pushed in the opposite direction. So the light coming by causes the electrons in the atoms to vibrate with the same frequency that the light had when it hit the metal. Now, that's exactly what's happening in the source. The source is giving off the light. The electrons are oscillating in a way that gives light of the same frequency that they're oscillating is being emitted by that source. So what happens is, when that happens to the metal looks just like the source. And that's why you see a mirror reflection. If I were to look at a light in the mirror, what I would see is the light bulb. I would see all the light all right, but I would see an image of the light bulb. That's what happens with metals. You see a shiny image as if the source were sitting there on the metal itself. Now, what's the difference? The reason why that works for metals is electrons move very, very easily in metals. And the metal electrons the electrons on the metal are not confined to an individual metal atom. Instead, they vibrate over the whole sample of metal. And that's what's making that mirror reflection. In the case of paper, paper is a non-conductor of electric current, which means every atom in there, its electron is staying stuck to it. And each one of them are different distances from the source. So each one of them is emitting all the light that hits it, but at a different phase. So what's going to happen is I'm going to see the intensity of the source, but I'm not going to see the image of the source. Now, that's the reason why metals have this luster. And it's also the reason why they're malleable, which means you can stretch them or you can pull them or bend them, hammer them into shapes. They're good electrical conductors of heat and electricity. I've already told you why. And they form ionic oxides, and they produce basic solutions when the oxides dissolve, if they do dissolve. Okay. They form cations as they react, and they have generally varying melting points. You probably know, if I said, well, there's only one element on the whole periodic chart that is a liquid at room temperature, all of you know I'm talking about mercury, probably. So there's only one liquid metal. And by the way, just since you brought it up, bromine is the only liquid non-metal. So there are only two liquids on the periodic chart at room temperature, one metal and one non-metal. Mercury is a liquid metal and bromine is a liquid non-metal. And the melting points can vary all the way from below room temperature to several thousand degrees. Tungsten that we used to use in incandescent light bulbs, you still do if you still got a few of them around. That has a very high melting point, which means I can pass so much current through it that it gets white hot before it even melts. And so the filament of the light bulb stays as a solid, even though you heat it to several thousand degrees. So some metals have 3,000 or 4,000 degree temperature melting points, and others, like mercury, melt even below room temperature. Now, on the periodic chart, the metallic character, if you look along those stair steps, again, I'll just read off a couple of them. If I'm looking at the carbon family, there's carbon, and under that silicon, then germanium, then tin, then lead. You certainly recognize lead in that group as a metal. You may know that tin is, although what we call tin cans that we put food in is not really made of tin. They're made of steel with a thin coating, used to be with a thin coating of tin. These days, they're apt to be coated with some type of polymeric material. But anyhow, looking at the carbon family, carbon at the top, tin at the bottom, obviously metallic properties increase going from top to bottom. Let's go, say I go across the third row. It's got sodium, then magnesium, then aluminum, then silicon, phosphorus, sulfur, chlorine, and argon. Now you certainly recognize chlorine and argon as gaseous, non-metallic types of materials. You certainly know aluminum and sodium and magnesium are metals. So metallic character increases from right to left across a row. And yes, it is from right to left. Okay. Now, metals follow a reactions called single replacement reactions, or you can have one metal react with a compound of another metal. The more reactive one would displace the other one. And we don't know for sure how to predict that, especially in aqueous solutions. So we have to do an experimental determination of which reactions happen and which ones don't to create an activity series table. So if we expect a single replacement, like M goes in, M1 goes in, and M2 comes out, then for that to happen, M1 has to be more reactive and higher on that activity series table than M2. We'll work on that in much, much more detail later, even in great detail in Gen Chem 2. The group 1A metals are very reactive. I've told you they react with water. The 1A metals will react with cold water. The 2A metals, the top elements, will react with steam, but they won't react with cold water. The elements in the bottom of that group 2A family, we're talking about beryllium, magnesium, calcium, strontium, barium, radium is in that family, but nobody in his right mind does chemistry with radium. It's way too dangerous. People who do wind up getting, well, most of the time they get what they used to call pernicious anemia, which is leukemia. And it's very, very reactive. I'll tell you a little story and then maybe we'll take a little break for a moment. I used to have a watch when I grew up that I thought was the coolest thing in the world. It had numbers on the dial that would glow in the dark. I could look at my watch. I could wear my watch at night, and I could look at my watch any time at the night, and I could still tell what time it was. It didn't have a little battery inside. It didn't have anything inside except the numerals that had been painted on that dial. they look kind of greenish in the daylight, and they glowed with a kind of greenish yellow glow at night. They were made, the paint for those numbers was made from radium. It was a radium type of paint. And they were painted back in those days, the watch dials were painted by hand. So the people who made the watch had people paint the little numbers on the dial by hand with a brush. Now, what do you do if you're painting? You shouldn't do it, but what most people do when that little tiny brush gets sprayed, they'll pass it between their lips and their tongue and get it moist and form it back into a little sharp peak and go again. Well, that's what those people did. You know what? Making those radium dial watches killed every single person who did it. Isn't that crazy? We do things sometimes we don't really understand, and we don't know we're hurting ourselves in doing it. But that wiped out a whole industry. And now, if you've got a watch dial that glows in the dark, it's probably not radium. It's probably a phosphorescent element of some other non-radioactive element. But they used radium back then. Okay. Some of the other metals do react with acids. Now we're talking about hydrogen sources. The least reactive hydrogen source we're looking at here is water, cold water. And then warm water would be more reactive. And then steam would be a still more reactive form of hydrogen in water. And then we can take, if we need something still more reactive hydrogens, we can use acids, because all the acids release H+ ions when they react. And so this can be used to sort out reactivity of other elements, is to see, well, for example, if I'm looking at 1A, lithium and all of those would react with cold water, but the ones near the bottom react much more rapidly. So I'm going to say the ones in the bottom are more reactive metals than the ones near the top. But if I go to group 2, the top ones will only react with steam. None of them react very well with cold water, but the ones near the bottom react with hot water. If I go to other elements, some of them react with acids and release hydrogen, others don't. And so you have to build an activity series. And if a metal reacts with water, it's going to release hydrogen like that. Or if it reacts with an acid, it would also release hydrogen. But remember, the metal's going in, the hydrogen's coming out. So there are some metals less reactive than hydrogen. Copper is one. It won't react with acids and this type of reaction. Copper does react, but if we want to dissolve copper, we can't do it with hydrochloric acid. We have to do it with nitric acid. And it's not reacting with the hydrogen, it's in the acid, it's reacting with the nitrate in the acid. Okay, oxides form hydroxides in water. And if they're soluble, not all metal hydroxides are soluble. There's a solubility rule that we'll mention more in detail later. And not very many oxides are soluble in water. Generally, all of group 1A oxides are. Some of group B, 2A are. 1A, all of them react, dissolve and form hydroxides that are soluble. And group 2, only a few of their oxides are soluble in water. And when you dissolve the metal oxide in water, you're essentially going to take the metal, it's going to react and form Ma2 in this case, if it's balanced the way I've got it, and then the H2O forms the water. And so this is the kind of reaction you get. It's not a single replacement, it's a double replacement reaction. Okay. And I think this is a good place to take about oh, I don't know. This don't take too long this morning. I need a lot of time. So let's take about a 5-minute break. We will convene at 9, 9 o'clock or shortly thereafter. Okay, let's escape from here and let's stop the share
Hey, Dr.
and,
Pearson.
and resume the recording. And then I want to share the screen again with you. Okay, this is what the first question was about, was the periodic chart and the places on the periodic chart. So we'll go ahead and run through this the PowerPoint way. Now, the first column of the periodic chart on the left, not really including hydrogen, but it's there because hydrogen behaves the way they do. They all form +1 ions, so hydrogen forms compounds where it appears the hydrogen is a +1. For example, HCl. Hydrogen is in the metal position, and chlorine is in the non-metal position. Chlorine from the periodic chart would be -1. That would make hydrogen a +1 in that compound. It would be okay to be there. And most modern periodic charts, that's where they put hydrogen. In the old days, when my periodic chart had hydrogen in 2 places, it also had it over here in 7A. And the reason for that is it does form a negative ion just like chlorine does. You can have sodium chloride or you can have sodium hydride. So it formed compounds like group 7 also. But in the periodic charts that you have, they only show hydrogen in group 1A in that column. But the rest of the elements in there are named by a family name called alkali metals. So if I wanted to talk about any of the elements in group 1A, I could just refer to them as alkali metals. I could say, well, alkali metals react with water to form hydrogen and the alkaline metal hydroxide. See, so I wouldn't have to say sodium, lithium, potassium, rubidium, cesium, or francium. I could just refer to the family name to describe family characteristics. And the family name, just like Smith and Pearson, those are family names. Well, this is the family name for group 1A, alkali metals. The second family, group 2A, is called the alkaline earth metals. And you would recognize the reason for the word earth is calcium and magnesium are the primary components of dirt. You know, sand and soil contain magnesium and calcium in them, often in the form of their oxides or silicates or some other formula. But they are elements of earth. They do form alkaline solutions. Again, I told you a while ago that the metals near the top of those elements would react with steam to release hydrogen and make the hydroxide. The ones near the bottom can do it with hot water, and they form a hydroxide, which is a compound that's alkaline in the sense of opposite to acids. So it's the opposite type of characteristic to an acid. So they're called alkaline earth metals. The other little stair step I talked to you about a while ago, these are all representative metals, and the ones above that are called representative non-metals as a group. And then they do have family names as well for some of them. Like these things here are metalloids. They're between metals and non-metals. They're all representative elements, but these would be metalloids, which means they're somewhere between metal and non-metals. If you look at the little, those elements that are in sort of orange on the screen, if you know anything about transistors and all of that, and semiconductors and chips, they're made of the elements that are in this metalloid family because they are able to behave as either metals or nonmetals depending on the voltage that's applied to them. And if that means that you can change them from plus to minus at a certain voltage when you apply it across them. And at the most basic level for all of electronics is a binary system where something is in represented as a plus or on or an off. So you can switch from plus to minus at some voltage. So if you send a voltage through a chip, you can change it from off to on, and you can change it from up to down, or whatever the two binary digits are, you want to call it. So you'll recognize transition elements. The metalloid elements are right in that group between the representative metals and the representative nonmetals. Group 7 family is called the halogens, and their compounds are halides. So I don't need to talk about, if I want to talk about the compounds of group 7, I can talk about the halides. And then it could be either it could be either fluorine, chlorine, bromine, or iodine, or astatine, any of those elements. And likewise, the family name for group 8 is the noble gases. When I was where you are, they were called inert gases, and I was taught they could never react with anything. Turns out some of them do react. And xenon has actually formed compounds quite easily. You can take xenon and fluorine and mix them together, and you'll get xenon fluoride. It happens all by itself if you set the container out in the sun and let it get a little bit of sunlight. So what I learned is inert elements, because they didn't fit my little octet rule, was wrong. So sometimes chemistry teaches wrong things. We don't intentionally do that. Sometimes we do, though, because we don't know. Okay? So now, the transition metals are the ones in between. So remember, all of them from this stair step down is metallic, and these are called transition metals. They start on row 4 on the periodic chart. This would be scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, or zinc would be the first row transition metals. And as I said, they transition from the elements property on this side to the elements property on this side. So the first one in the transition series is very much like that one. The last one is very much like that one, and not very much like the one on the left at all. Okay. All right. And the bottom one is called inner transition elements, and they're called inner transition elements because this first row that goes across here from cerium to lutetium is that first row. They belong between lanthanum and hafnium on this row. So all 14 of these land between the first of this transition series and the next element in this transition series. Similarly, the bottom 14 elements fall between actinium and rutherfordonium, a new element that's not been made very long, but they fall in that gap between them. And that's why it's important that you use a periodic chart like the one I give you, not the one you're apt to find in online and in other places. Okay, because that little gap right there is where these two elements belong. Okay. Let me just click through some of this because I think this is all that you can read easily. And okay. And it gives you some of the characteristics of some of the elements and families of elements. And this family of elements becomes critically important to us because if you remember, we talked about a periodic table. These things are, I mean, in our thinking, they're sort of in the middle. You're going to take metals that try to become the noble gases, and you take the non-metals that try to become noble gases by gaining electrons. And once these form, they are extremely stable. So I mentioned the fact that your cereal doesn't have sodium in it. It would catch fire if it does. It would have sodium ion in it, but we name the ion and the metal the same, although they're not certainly the same. But the sodium +1 ion, the reason why it's stable and you can put it in your cereal is because it has lost an electron, and as far as the world is concerned, it's the same as neon. And neon hasn't ever been able to react with anything. So sodium ion doesn't react with anything. Okay. Now, I'll do a couple of these just for illustrations, but you can look this up and practice on this as well. Remember, do not Google these things. You'll get them in the correct order, but it'll be wrong. Remember, we're going for the expected trend off the periodic chart, not what it really actually is. So if I'm looking at metallic to non-metallic in an element, what I'm looking for is where is it located on the periodic chart. Remember, the metals are below that little stair step on the right, and they become more metallic going from top to bottom and more metallic going from right to left across a row. So whenever you're doing rankings, it's always easy to pick out which is the largest and which one is the smallest. So if I'm looking at this, the most metallic element in that bunch is gallium. It's element number 31 on the periodic table, and it's further into the metallic region than any of the other elements. In fact, AS and SB and TE are, again, on the non-metal side of that chart except for SB, and it's below. Okay, now to get the, actually what I would have done, I think, is pick the two extremes first. I did them in order from most metallic to least because that's what we were discussing. But if I'm looking on the periodic chart, the most metallic element certainly would be gallium. And then the least metallic of the bunch would be arsenic. And then SB and TE. Now, predict the form of the oxides, whether they're ionic or molecular. If you've got a metal with a non-metal, it's ionic. If you got non-metal with non-metal, it's molecular. So this is an ionic, this is molecular. I'm sorry, ionic, molecular, ionic, molecular, molecular. So you can look at those. Metal with non-metal, ionic. Non-metal with non-metal, molecular. Non-metal with non-metal, molecular. Okay, all right. Which is more reactive, aluminum or indium, sulfur or selenium? Well, aluminum and indium are in the same family. So which one would be the most metallic? Indium is below aluminum. It would be more metallic, wouldn't it? Sulfur and selenium are in the same family. Sulfur is over selenium. So we're going to think about these and non-metallic reactivity. And that means sulfur is more non-metallic. It's nearer the top than selenium. And so most reactive of the pair would be those. Okay. All right. Should a reaction occur between indium and sulfur, what would the reactant formula be? Well, the most metallic element is going to be indium, and the least metallic is going to be sulfur. So indium is going to be in the first part of the name, like a metal, and sulfur is going to be the second part of the compound. And if I'm looking at indium, indium is in group 3A as a metal, it would be a +3, and sulfur would be a -2. Because of its position, it's in group 6, it would gain 2 electrons to go from sulfur to argon. So it would need 2 electrons, so it's -2. And so I've got a +3 ion with a -2 ion. So the expected compound is In2S3. That is what we would expect. That would give you a neutral, no charge species if you put those two together. And we could write a reaction like that, and then we'd have to balance it. And we've learned about balancing equations already now. Okay, now, so that finishes everything that we need for exam 3. So I want to pull up the practice exam. Oopsie daisy, I don't want to pull that up. And I'll show it to you when I get it all ready to go. Where is my practice exam? Well, I thought I must have closed that out a while ago. Okay, now I've got it. And now I need to go to screen share and share a new one with you. Okay, now some of you have already asked questions about the practice exam. So if you would like, maybe I would prefer to answer your questions exactly and answer them first, and then we can use the rest of the time just to go down through. Is there any one of them that you would like to ask me about?
I'm just confused. I know you went over this earlier, but I'm just confused on when to use Roman numerals and when to just use the subscripts.
Okay. If you look back at the PowerPoint lesson on that, the Roman numeral is not required. Let me see. I'll see if I can stop share a moment and get back over here. Now, if you have on the periodic chart, I'm going to say no Roman, R-O-M-A-N, no Roman. Okay, that's group 1A. And you know what I'm talking about there? That's lithium, sodium, potassium, rubidium, cesium. If it's one of those elements, it doesn't have a Roman numeral because all of them are always +1. They can't be anything but +1. Group 2A does not require a Roman numeral. They are all +2. So if I take beryllium, magnesium, calcium, strontium, barium, any of those elements in that family, their only possible charge is +2. I don't need a Roman numeral in the name if it can't be any other charge than that +2. So I don't need, there's not going to be a calcium +3 or a calcium +1. It's only going to be calcium +2. So it does not need a Roman numeral because I know if it's calcium, it's +2. I know if it's barium, it's +2. If for some crazy reason somebody's made a compound with radon, I know it's going to be a +2. I'm not going near it, but it could. So no Roman numeral for 1A, 2A. The other one is zinc, because zinc is +2. Aluminum is always +3. Zinc, cadmium, zinc +2, cadmium +2, aluminum +3, and silver, Ag +1. And I think, okay, yes. There are 4 other individual elements that don't require a Roman numeral if they have this charge. Now, it is possible to make compounds of different charges than this, but it's very difficult and very unlikely. Zinc is going to be +2 anytime you see it. Aluminum is going to be +3 anytime you see it. Silver is going to be +1, and cadmium is going to be +2. Now, this is a memorization. You have to memorize that. No Roman numeral for those elements. All others, that is the cation, the positive ion, all others require a Roman numeral. So, for example, if I saw AlCl3 as a compound, I'm just going to call that aluminum chloride. Don't you call it aluminum trichloride. I'll count it wrong every day. The prefixes are only for non-metal compounds. Even though you Google it and you can find aluminum trichloride on the internet, it is not correct. It is aluminum chloride, period. Okay? Now, if I had iron as the chloride, there are 2 compounds I could have. I could have iron, FeCl2, or I could have iron, FeCl3. Those are the 3 likely compounds of iron. I'm not saying there couldn't be some other compound of chlorine of iron, but this one, iron, is in what charge? Well, chlorine is -1. There's 2 of them. So iron has to be +2 in this one. Chlorine -1, there's 3 of them. So iron has to be +3 in this one. This one would be called iron, Roman 2, chloride. And this one would be called iron 3, chloride. So any other than this family and this this 1, 2, 3, 4 other elements don't need a Roman numeral. Everything else does. Okay?
And then you said the prefixes are only used on the nonmetals?
On nonmetals, if I had something, well, let's take an example. CO, you already know. What is it? Carbon monoxide, right? Carbon dioxide. You use the prefixes with non-metal compounds. Non-metal compound. I can have Cl2O3. That is a possible compound. Non-metal. Now, I can name these the Roman numeral method if I want to. I could call oxygen -2, so this would be carbon in the +2 form. I could call that carbon 2 oxide. Here, -2, -4, carbon would be +4. This could be called carbon 4 oxide. But most people are going to think you're weird if you do that. You know that's carbon monoxide and carbon dioxide. And similarly, that would make this the +3 form. You could call this chlorine 3 oxide, not chlorine 3 trioxide, chlorine 3 oxide. So, and that would be okay. But you won't sound quite as weird if you call it dichlorine trioxide. So in non-metal compounds, the preferred nomenclature is the prefixes. Mono, di, tri, tetra, where'd I get to? 4, penta, octa, penta, hexa, hepta, octa, nona, deca. Okay, you could do those, but if it's a non-metal, use that form of nomenclature. Although I would not count it wrong if you use the Roman numeral. That's the more modern one, and it's coming to be more acceptable. But most everybody are still using these. But I can tell you now, if you Google this formula on the internet, it's probably going to call it iron trichloride, and I'll count it wrong. Okay?
Thank you, Dr. Cooper.
You're welcome. Any other general questions or specific ones about the test?
Can I ask a general question?
Yes.
On the review, it doesn't have any problems for the material that we covered today. Should we assume that the material from today is on the test or is not on the test?
It's not. If it's not on this test, it won't be on your test. I mean, just think about the mechanics. Hey, I'm kind of a lazy guy. So what I'm going to do is take your practice exam and just change the questions to another one like that. The first one's not going to be convert minus 15 degrees Fahrenheit to Celsius. It might be convert minus 15 degrees Celsius to Fahrenheit, or it could be minus 27.8 Celsius to Fahrenheit, or it could be, it'll be a temperature conversion. And then number 2 is going to be a complex unit conversion. And by the way, on some of the checkpoints, I've really very carefully had you learn a particular method for unit conversion. And the way it is, you've got in the problem, you'll be given some number, an amount, and it will be in some given unit. And if we want, and then it'll ask you for the amount in some other unit. And we're going to do it by a conversion factor, and we're trying to do it, if possible, in one conversion factor. The way we would do that is we would copy that unit down here, given unit. And we would look at the problem, and it's going to say how much, blah, 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 blah. That's the ask unit. So you're going to have an ask unit. And now all of this is in the problem. And it'll say a number here, 57 inches. So that's a 57, that's inches. Inches are going to go here. It might say, how many centimeters in 57 inches? Well, you'd put 57 inches here. You'd put inches here. It said how many centimeters? You'd put centimeters here. And then you'd have to remember that 2.54 centimeters is 1 inch. And you put those numbers in here. So there's a number that goes here and a number that goes here. This many of these is equivalent to that many of those. And when you set it up and do the math, you get the answer. So I want you to use that scheme everywhere you can, because it's the quickest setup and with the least number of operations. I think on the checkpoint was to the sodium sulfate, and it was to convert, suppose you had a sample that had 2.5 grams of sulfur, I think it was, and how much oxygen would you have in it? Well, you should be able to set that up in one conversion. Some people took the 2.5 sulfurs, and they took the 2.5 grams of sulfur and calculated what the weight of the total compound would be, from analogy to the one we worked on in the course. And then they took the weight that they just got and converted it to the grams of oxygen. Now, there's nothing really wrong with doing it that way, except if you would look at your numbers, the numerator and the denominator of the two factors were the same. They would have canceled out. You don't need to go through those others. All you're looking for is how many of these is equal to that many of those. And if you know that answer, you don't have to go through multiple conversions to do that. You just do it in one. And this is an example. We're going to convert pounds to grams. The conversion factor that you're supposed to know is it's 454 grams is 1 pound. And you're going to convert inches to centimeters. You have to remember that 2.54 centimeters is 1 inch. And then you have to square to do this part of the conversion. So you should come out with, if it's pounds per square inch, grams per square centimeter would be the correct answer. And I guess if you do the math. Now, this one is still causing people problems. And I've tried to be really, really detailed in grading the checkpoint on this one. Now, this is, and I want to say right now, right up front, when do you round off a number? The only number you round off is the answer. The only number you round off is the final answer, not the intermediate calculations. Do not do that. I counted off for it. Don't do that. You only round off one number, the final answer. There's two parts of round off rules. If the problem involves addition and subtraction, the very last answer has to be the one with the least number of decimal places that you're adding and subtracting, not the least number of significant figures. That's multiplication and division. So I've separated it here in this problem. If I add this number to this number, then when I add these together, I'm going to have the 0.2400. There's 4 decimal places in this number. It does have 4 significance, but that's irrelevant to this problem. It has 1, 2, 3, 4, 5, 6 significant figures in this problem. It's irrelevant. It's an addition problem. This one has 5 decimal places. This one has 4. The answer has 4 decimal places. So when I add these two together, I'm going to get 1.24246, and it's going to have 4 decimal places. So 4 decimal places plus the 1 is 5 significant figures. And I'm not showing you the screen while I'm doing that. I'll go back and get it. This is what we're talking about right here. This particular problem, you don't worry about the significant figures here or here because it's only addition. This has 4 decimal places. This has 5. The answer will have 4. So it'll be 1.24246 when I put it on my calculator and add them. I'm going to keep the 4 decimal places plus the 1 is 5 significant figures. So that is the number of significant figures in the answer. Now this one, next one, it does involve a multiplication and division and an addition. The addition is the last thing that gets done. It's going to be rounded off by the multiplication and division rule. So if I divide, I don't want to do it on the screen because I'm going to have to correct the answer down below and save it. So when I divide, I'll just tell you what I get. You can follow me on the calculator if you want to. Take 46.666 and I want to divide that by 15. And I want to divide that by 15. Okay, I'm going to check my screen. 46.666 divided by 15. That's going to be 3.11106666667. That's what my screen is showing me. If I were done, how would I round this number off? Well, there's 5 significant figures in the numerator and 2 in the denominator. The answer would have 2 significant figures. I'm looking at my screen. 2 significant figures would be 3.1. So it has 1 decimal place. This number has 1 decimal place. This number has 2. The answer has 1 decimal place. You know what? I'm done right now. I don't have to do the math. There's only one of these numbers that has 1 decimal place. That's the answer. And this one down here, I've got 3.6. I've got an addition. That's the last thing it's done. So I'm going to do this calculation here on my calculator, and I'll tell you the results. I take 3.6, I multiply it by 1.444, and I divide it by 6.66462. Okay, I'm reading it off. Check it. 3.6 sounds 1.444 divided by 6.66462. I've entered it correctly. All right, the answer to this part of the problem, and we're looking at it right here. The answer to this part of the problem I'm seeing on my screen is 0.7799994598. 0.774 and 4 nines. How would I round this off if I were done? Well, there's 2 significant figures in the first number, 3.6. There's 4 significant figures in this next number, and there's 6 significant figures in this one. This would round off, if I were done, to 2 significant figures. I'm looking at my screen. 2 significant figures would be 0.78, but I'm not going to round it off. I'm going to notice that 0.78 has 2 decimal places. All right, now let's go over to the left. Remember, 2 decimal places. Over on the right-hand side, 7.1234 divided by 0.63466. 7.1234 6346 466. I've entered it correctly. The right-hand side, the answer is 11.22419942. How would I round it off? I've got 1, 2, 3, 4, 5, 6, 7 significant figures here. I've got 1, 2, 3, 4, 5. The smallest is 5 significant figures. So I'm looking at my screen again. 11.22419942 to 5 significant figures. 1, 2, 3, 5 significant figures is 3 decimal places. This number has 3 decimals in it. This number had 2. The answer is going to have 2 decimal places. So let's do the math. I take the number that I just calculated. I'm going to add to that 3.6 times 1.444 divided by 6.66462. And my answer is 12.00419888. My answer is supposed to have 2 decimal places because that's what was in this one. This one had 3 decimal places. The answer has 2. So 2 decimal places is 12.00. That's 4 significant figures. Okay. Now that's the way you do that. Do not round off the intermediate numbers. That did cause somebody to miss the problem, I remember, when I did a checkpoint. They rounded off some numbers in between and they didn't get the correct answer. They got a slightly different answer. And so I didn't give credit for it. Okay, temperature conversions, you know how to do that. Again, I prefer you do the add 40, convert, subtract 40 technique that I showed you in class. If you do it by the C is 5/9 F minus 32, or however it is. I don't remember. I have to derive the stupid thing every time I use it. And believe me, if you remember it now, you won't a few years from now, and you might not on the final exam. And I don't really know how you got the answer. The correct answer is A. Do it however you want to. But I want you to learn a method you'll remember 2 years from today. Convert to Kelvin, you add 273.16 to that. Nuclide symbols, you've had a checkpoint on that. As I recall, believe everybody got at least two. Oh, everybody got at least 3 of the 4 things that we had to have. We had to have a symbol for the element. We had to have a lower subscript mass atomic number, a left upper superscript, the mass number, and a charge number. Excuse me. It is a cation because it's charged. How many neutrons? Well, you subtract this number from this one. That would give you this one. The one that some people missed was maybe they just forgot to put the charge on. But if this is +3 and it's got 77 protons, it's got 3 fewer neutrons. So it would be 74 electrons. Okay, and that's the point of this question here. Now, this is a law of multiple proportions. Oh, something. See, I think I need to get it a little bit bigger so it shows everything on your screen. Okay. Allergies give me a little tickle this time here in my throat. It's hard to get out. Okay, 2 different compounds exist containing only chlorine and oxygen. One compound is 59.66% chlorine and 40.34% oxygen. According to the law of multiple proportions, which of the following percentages is possible for another oxide of chlorine? Okay, remember how we have to do the law of multiple proportions. We have to get the amount of chlorine the same in all of my samples, and the amount of oxygen, how much it would be for that same amount of chlorine. Now, in this particular compound, say if I had a 100-gram sample, it would have 59.66 grams of chlorine and 40.34 grams of oxygen. Let me stop the share a minute so you can see my screen, and I'll set that up for you. Okay. All right. My reference compound in the problem, number 10, the reference compound has 59.66%, I'm going to say grams out of 100 of chlorine, combined with the difference between that and 100 is 40.34 grams of oxygen. Now, I want to get a number 1 for this first one. So if I divide that number by 59.66, I would have to divide that number also by 59.66. This would give me 1 gram of chlorine combined with whatever I get for the math over here, 40.34 divided by 59.66, and that would be 0.676, 4 significant figures. Next one is 1/6, so this would be a 2 grams of oxygen. Now, my different compounds. Well, I do them in order, so I'm going to go ahead and do number 1. That's supposed to be the correct answer. Then we'll try one of the others. It says we've got 81.61 percentage of chlorine. So let's make that grams out of 100. Now, how much oxygen would be there? Okay, it's the difference between 100 and this. So it's 100 minus 81.61. And now I need to get a 1 here. I divide this through by 81.61, and that'd be in grams of chlorine, and divide this by 81.61. I'm going to get 1 gram of chlorine here. How much over here? Well, it's going to be 100 minus 81.61, and that is 18.39. And now I want to divide that by 81.61, and this gives me 0.22534. The next digit would be a 3. Then I just dropped the 4. Okay, so grams of oxygen. Now, if this one is correct, I've got the same amount of chlorine in this as in the reference compound, but I've got this much in the A and this much up here. Now, if this is correct, these two numbers should divide out to be a whole number, or the ratio of whole numbers. That is, if I take 0.6762 and divide by 0.2253, well, what would I get? Well, I've got the 22534. I've got all the digits. So I won't worry about that. So I'm going to take that. I'm going to take 0.6762 and divide by the answer I've got still stored. And what I come out with is 2.996. Okay. Now that's not a whole number, but it's within a change in that digit. If that had gone up above 10, that would be 3. So if I were going to round this off to a whole number, the whole number would be 3, and it'd only be 4 parts in the last significant digit that would make that happen. That is an acceptable answer. So A is correct. Let's look at B. It's kind of cute. Let's try B. And I need to get this up where you can see it. In B, I've got 18.39 grams of chlorine. How much oxygen would that be? Well, I would have the difference, 100 minus 18.39. And I want to divide this one by 18.39. Give me a 1 here. Divide this one then by 18.39. Here I get 1 gram of chlorine combined with how much oxygen? Well, 100 minus 18.39 is 81.61, like we had up here. So this is 81.61 divided by 18.34. This gives me 4.49836.423 if I didn't copy something incorrectly. Now, according to the law of multiple proportions, my reference amount in my reference compound was this. So this and this should be a ratio of whole numbers. So if I take this number and divide that by 0.6762, so divide that by 0.6762, I come out with 6.5 806. You see, there's no way I can round off this to a whole number without affecting this digit. And that that digit is the third significant figure. It's got to be in the fourth to be rounded off okay. So I'm not going to call that a 7. It's not a 7. It's a 6.521 if I wanted to round off out there. So that's not the right answer. So B is not correct. Okay, so now that's how you handle the law of multiple proportions. And again, we've done some practice with it and worked some examples and stuff. Okay. All right. Percent by mass of oxygen in SO3. Are we okay with that for all of you? Well, I'll ask the question another way. Is there anyone that's not okay with me skipping number 11?
I got it. I'm good.
Okay, very good. Okay, number 12. Now this one, a formula weight, that's just straightforward. Again, you're going to take 3 times calcium. There's the calcium atomic weight you're to use. You're going to have 2 times 1 phosphorus. That's the atomic weight you use. 2 times 4 is 8 times 16. That's the oxygen. Add them all together, you get 310. So I don't think anybody would have had trouble with that one either. Now, I will set this one up and work through it with you because, like I said, there are some people that have had trouble with doing this kind of stuff in one significant one conversion. And I do want you to be able to do that. I'm going to see if I've got a better pen over here already open. And if I do, it'll be better. If I don't, I'll switch back to that one. Okay, we're doing number 13. And I'm going to stop screen share so you can watch my pad. So for number 13, remember it's a conversion factor. So it says, given this formula, there's the formula, generate a conversion factor and determine the mass of phosphorus in a 1.5 gram sample of the compound. So I've got 1.50 grams of Ca3PO4 2. And now, how did we say? This is the given amount. This is the given unit, grams of this. Always when you're using grams, tell me what you're weighing. Because when you get over here and you start canceling out grams, if you've got grams of compound and grams of oxygen up here, they're not going to cancel. So I've got to have the same unit here as I've got here. If I just put grams in here and grams in there, any set of numbers would work. They'd all cancel. But now, what did we do? We said, okay, we're going to copy this amount right there, that unit. So I want grams of Ca3PO4 2. Now it says, determine the mass of phosphorus. So I want grams of phosphorus up here. Okay, now, what numbers go here? Okay, I guess I'm going to have to figure out the molecular weight after all. You know what? I'm going to go use the answer we had above because we just calculated that, and I know you all know how to do this. So we got 310.2. So 310.2 grams of that compound. How much phosphorus would it have? Well, again, look at the formula of the compound. For every formula unit, this much, of this, how much phosphorus? 2 phosphoruses. 2 moles of phosphorus. The atomic mass of phosphorus is 30.97. Okay. Now, all I got to do is do the math. My units have canceled out. The unit that I've got showing is the unit in the problem. When I do the numbers, I got to get the right answer if Dr. Pearson didn't mess up and not put the right answer on the test. That I don't do it on tests, but I have done it on here before. 1.5 times 2 times 30.97 divided by 310.2. Let's see if I've got my numbers entered right. 1.5, 2 times 30 divided by 30.97, yeah. That was a gram, not a number. And then 310.2. Okay, looks like I've got it set up right. And my answer comes out to be 0.299516441 grams of phosphorus in that amount of compound. So I've got, looks like 4 significant figures. No, my problem had 3. So I'm allowed 3 significant figures. So it looks like that would be 0.300 grams of phosphorus. I'm dropping something bigger than 5. Yeah. So the correct answer in this case is B. Okay. Now, I hope you looked at this as all of these kinds of problems, every one of them, will work the same way. I'm going to make up another one for you here just to see that you understand. I call it 13A, which could be on your test. Don't take that as a hint. It could be, but a sample of Ca3PO4 and I would be kind to you on this test. If it were on the final, I would just say a sample of calcium phosphate. And you'd have to be able to get that formula. Okay, but not here. Is found to have exactly 1 gram of phosphorus. What is the mass of oxygen in this sample? Okay. Now, that doesn't look like the other problem, but it is just like the other problem. Given amount, 1 gram of phosphorus. I want to put that unit here. And it asks how much oxygen. I want grams of oxygen here. Now I'm looking at how many grams of phosphorus are there in calcium phosphate? Well, there's 2
I'm
moles.
sorry, can you scoot the paper up just a little bit?
Raise the paper.
Oh, you're not seeing it. Why are you not seeing it? Okay. Are you? You are
You
seeing
can
it
see the
now,
paper
right?
was just too.
Yeah,
You're-
perfect, thank you.
Okay, very good. Thank you. All right, so now I'm looking at my formula. There's 2 moles of phosphorus. So phosphorus value is 2 times the molar mass, or atomic weight is 30.97. And grams of oxygen, well, how much oxygen? There is 2 times 4 is 8 oxygens. So there's 8 times 16.00 grams of oxygen. This is from the atomic weights. All right, now my units cancel correctly, and I can do this math. It's 1 times 8 times 16, so it's just 8 times 16 divided by 2 and divided by 30.97. I get the answer is 2.066515983 grams of oxygen. That's the unit that's left. Okay, now, how would I do round off? That's an exact number. Problem said that was an exact number. 2 is an exact number. There's 4 significant figures in each one of these. My answer would have 4, so it would round off right there. So it's 2.067. That's bigger than 5 grams of oxygen. Okay, now I'm asking a question. I hope you answer for yourself. You don't answer it for me. Do you see that these two problems are the same? If you do, you've got it, and you'll be able to work this problem on the next exam and on the replacement exam and on the final exam. If you see that these are the same problem. Okay? That's really the reason why I do what I do, is I'm trying to get it so that something makes sense to you reasonably. Now, there's lots of ways you could go about working this problem, and it's multiple choice. So if it's on the exam coming up, it will be. There'll be one like that. But if it is, it's going to work exactly like these do, but it might not look exactly like that problem. It could be anything having to do with a formula and masses of elements in the formula. Okay? But there's lots of other ways to work that. Sometimes in a panic, you might use one of those others if you don't remember or draw a blank. I've done that. But if you remember, then it'll be a lot easier. Okay. Okay, this is exactly the problem I just worked, except it's with a different compound. So it's a more complex compound. This looks kind of weird, but when I worked for Shell, I worked with a lot of compounds like this, where there was something stuck to a metal and it was in the cation, or something stuck to a metal that was in an anion form. But this is really an exercise more of, can you unravel all of this? So, and oh my goodness, it's almost exactly the same problem. Let's set it up over here. I'll do the setup. I don't think I'm going to work through all the answers on this because we just did one very much like it. So let's stop screen share. And okay, and we are here for number 14. I think I've got 2 pages of paper here. Yeah, no, I don't. Okay, number 14. And it says you've got a sample that's 1.500 grams of cobalt in that sample. And it wants to know what mass of oxygen. So here's what I'm going to do. I'm going to take this. I'm going to put grams of cobalt here, because that's what that's to cancel. Problem asks for grams of oxygen. I'm going to put that there. Now I've got to have some numbers. I'm looking at the formula of the compound. In the first one, I've got 3 cobalts in the cation, and in the anion, I've got 2 more. I've got a total of 5 cobalts in the compound, and it tells me the atomic weight is 58.93, so I've got 5 of them times 58.93. Now, oxygens. I've got to get the oxygen. On the left side of the formula, I've got 4 times 3 is 12 oxygens. In the anion, I've got 3 times 4 is 12 times 2 is 24, I think. I'll double check that. Let's just double check. So I've got 2 times 3 is 6 times 4 is 24. That's right. So I've got a total of 36 oxygens in it. So it's 36 times 16.00. Get my significant figures. Now my grams of cobalt cancel. I'm ready to do the math. So my math is going to be 1.500 times 36 times 16 divided by 5 and divided by 58.93. And the answer units is grams of oxygen. So let's do my math. Well, I said I wasn't going to do it, but I will. 1.5 times 36 times 16. I will if I can turn my calculator on. Okay, now I'll do it. 1.5 times 36 times 16 divided by 5 divided by 58.93. I get 2.93229.255 as my final answer. And I look at my answers. 1.500 is 4 significant figures. Infinite, infinite, 4 and 4. Answer should round off to 4 significant figures. 1, 2, 3, 4. Should be right there. 2.932. Okay, well, I didn't round off correctly on the problem, but 2.93 is correct, but there is another possible digit that would be correct. Sometimes they're not rounded off exactly right on the test, but I've done that for a reason. Sometimes some of the wrong answers would be given away if I gave that other significant figure. Nomenclature on number 15 we've talked about already. Name of this compound, it's potassium because that is the element, it's in group 1A, does not need a Roman numeral. It's just called potassium something. And this ion, if you remember, it's from studies, Cr2O7 is dichromate. So the name is potassium dichromate. That is correct. And we did number 17 already. Now this one is a hydrogen binary acid, hydrogen with tellurium. If you have one like this, think about HCl. You know that's hydrochloric acid. So this is going to be hydrotellurium. So telluric. We don't take the whole name. We just use the T-E-L-U-R, L-L-U-R. Yes.
Which screen are we supposed to be able to see right now?
I'm sorry?
Are we supposed to be able to see your screen or the paper?
Oh, thank you again. I'm sorry. Yes, you are. And I keep forgetting I have to switch it back. I wish I didn't have to do that. Wish I could do 2 screens. I guess you probably could if I wasn't such a, if I were a techno geek, I would have it down. But I'm not. I'll tell you a story about it. Actually, I have about 30 hours of computer science. And at that time, it was all about computer languages. So I can, at least at one time, I could speak about 5 or 6 different computer languages, and I could program all the way up into I could do assembly language. I could do some of those mean, nasty things that people do with viruses. I know how to do them, or did back in those days. But I've got not a clue about how to write an app to do something or other. So I'm kind of at the mercy of these things now. So I don't really know and haven't kept up with all of that. But I used to be pretty good at computers. Right now, if I plug it up and it don't work, I'm kind of clueless as what went wrong. So I've got a better set of headphones with a better microphone that came in yesterday. And when I plugged it up this morning, it didn't immediately start working. So I got to figure out, I know it's got a driver somewhere that I got to find before it's going to do it. But okay. Anyhow, this is the one we were talking about. We've already mentioned it. If this were a binary acid, it's going to be named hydrostemic acid. If it's just H with just one element here, or if it's H with cyanide here. If the anion ends in IDE, and telluride would be the anion form of tellurium, or cyanide would be the CN minus correct name for it, and they would all name hydrotelluric acid. If it's HCN, it would be hydrocyanic acid, and that's the correct name. All those other names are possible for other compounds, except ACIT. That's just a misspelling, and D, it was supposed to be ACID. Okay, I'll correct that right now. It might be correct already on D2L. I don't remember which form is there. Okay, which of the following ions is the bioxalate ion? Oxalate is C2O4 2 minus. If it's got a Bi there, it means it's got hydrogen with it as a positive ion. So it's HC2O4 1 minus. H is a positive ion. So plus with C2O4 minus 2 leaves a net charge of -1. So this is the correct name for bioxalate. Name of that compound, it's a nickel compound. It has to be a Roman numeral name. So trinickel diphosphate is absolutely wrong. But if you Google it, I'll bet you find it. Okay. And now, how do we get the charge of nickel? This is PO3 phosphite. PO3 3 minus is phosphite. So ITE is the correct ending, phosphite. So it's not that one, and it's not that one. So it has to be one of these two. And now, what's the charge on the nickel? Well, phosphite is -3. This is -6. There's 3 of them here, so nickel is 2. So it's nickel 2 phosphite, because the nickel is in the +2 state. The name of that acid, okay, it's not HCl, so you don't have hydro in its name. I can eliminate that acid right now. That's wrong. Now, we name it by the anion. ClO2 is chlorite, ITE. The acid is OUS, so chlorous acid is correct. Many grams of, unless it's, does anybody want me to work number 22? It's just like the 2 we've already done.
Yeah, I'm good.
Okay, all right. All righty, then let's go. The molar mass of this, does anybody need me to work that one out? I'll just tell you verbally, you've got 3 uraniums, 2 phosphoruses, and 6 and 8, 14 oxygens. Add them all together, looks like it comes out to 1,000 or something rounded off to 1,000. This one interpret this, and again, it's 2 times 3 times 4. 2 times 3 is 6, times 4 is 24. So the mercury's is 24. It's one of these two. How many phosphorus is 2 times 1 times 4 is 8. So that we're done right there. It has to be this one. We've eliminated this one already. So has to have 32 oxygen, so we could double check and see if it does. It's 8, 4 times 8 is 32. Yes, it does. It's like a lab experiment. But we've calculated density before. So all we've got is we got an empty beaker. We got a beaker with 25 milliliters of ethyl alcohol. There's the weight with the beaker and the alcohol. We subtract, we get the mass of alcohol, and we've got the volume is 25 milliliters. So the mass divided by 25 would give you the density. That looks like a good number to me. Say practically, if I didn't even want to work this problem out, I would be pretty sure it was not either one of these two numbers because I'm comparing it with water. Water's density is 1 gram per milliliter. This is going to be less dense than water. Because if I added 25 grams of water to that number there, I'd get 157. I got less than that. So I know its density is less than water. If I know that, I know the only answer it could be is B. The reason why I'm telling you this is sometimes if you can reason through an answer, especially on a multiple choice question, you can get there a lot quicker than you can by actually working it out. So sometimes the best way to get the right answer is to eliminate all the wrong answers. That might be the quickest way in some cases. I'll bet, how many of you want me to skip this one? I'm not hearing anybody. Okay, maybe everybody needs to see this one. Let's see. I'll pretend you weren't just bashful. Okay, let me get this so that you can watch my pad and I can watch the problem. So what do we got in number 26? We know that 4 widgets, I'm just going to call them W, weigh same as 7 thingamajigs. Well, that's T. So 4W is 7 T's. If 9T weigh 15.62 grams, what is the mass of 25 widgets? Okay, now I want to show you this is the same as the other problem we've been working. We got 25 widgets. So we got 25 widgets. And I want to find out the number of grams for the determine, student determines 4 widgets, what's the mass of 25 widgets. So I want the mass of 25 widgets. So I want widgets here, and I want thingamajigs here, and I want to know the amount. Well, I know that 4 widgets is going to have the same mass as 7 of these guys. So now this is going to be the equivalent number of thingamajigs to 25 widgets. I'm going to need another factor. I want to go from thingamajigs to grams. And I know that 9 of these weigh 15.62 grams. So let's see if my conversion factors are true. I didn't put my 4 down here. 4 widgets. Well, that was supposed to be a 4. 4 widgets is 7 thingamajigs. Okay, so my widgets are canceled. Now I've got thingamajigs. I know 9 thingamajigs weigh that many grams. So my thingamajigs cancel. And so my math is 25 times 7 times 15.62 divided by 4 times 9. Okay, now let's do the math and see what we get. 25 times 7 times 15.62 divided by 4 and divided by 9 is 75. Going up there a little further. 75.9305556 grams is my answer. And I guess I'm rounding off to 4 significant digits since all the rest of the numbers. Yeah, 25 widgets is a count. So the 25 is not 2 significant figures, it's infinite. So the only digit that has significant figures in it is the 15, there's 4. So that's going to be my answer. 15.93 should be the answer. And if I go back and share screen with you. Okay. Now, did you guys all see how that went? It was the same type of problem we did for all the conversion factors. All of them have been worked by the same method. You start out with a given amount of one substance, and you then convert using conversion factors to whatever else you have to do. Do it in one conversion factor if you can. That one was set up where you couldn't. You had to do 2 conversion factors to make that one work. Okay. Now, 27. Now that's a balanced equation problem, and I put it on the test here as the last problem on the test. On my exams, they're going to be in a different order for everybody in the class. So everybody's questions will be probably be scrambled. I know the answers are, and maybe the questions are too. So, but if this problem comes up number 1 on my test, it's going to be the last one I do. I'm going to work everything else and work this one last, because this one could take time. And if I run out of time, I'd rather guess at a correct answer to 1 question than miss 3 that I didn't have time to finish. So be really, really sure that you are wise with your time. I always tell people the smart way to work a test is you go through it once and pick the low-hanging fruit. Every question you see that you can just read and you know the answer to it, mark it and go on. And do that for the first pass through. That shouldn't take but just a few minutes, but you might get 2 or 3 or 4 questions already worked. You don't have to put any time in on them. Okay, as I go through a question and I don't immediately know the answer, but I know how to get it reasonably quick, I'm going to pick that on my second pass, do that one. And the ones that I'm saving till last are the ones that I either don't have a clue on or know it's going to take me a lot of time to get them. If it's going to take me a lot of time to get them, I'm going to work those as far as I go. And when they give me the 5-minute warning from D2L, I'm going to go in and start guessing on the ones that I've not done yet. Don't leave anything blank. That's an automatic wrong. But if it's A, B, C, or D, you look at it and see if there's a question you can eliminate. If there's an answer that you can eliminate, then guess from the others. If there's 2 questions you can eliminate, then you know that the answer is one of the other 2. Got a 50-50 shot at it. Guess. So that's the way, the strategic. This one I'm going to save till last. So I'm assuming you want me to work through this one with you. You might want to notice that the way I put the answers in there, there's not much of a way you can guess just by looking at it which of these answers is correct. So you're almost going to have to balance it in order to figure out the correct answer or eliminate the other ones. I won't tell you which one it is, but there's one of the answers that I'm pretty sure is not correct. Okay, let me, let's see, you're seeing my screen. I need to stop share in order to work this out with you. You know, I'm going to turn my paper the other way before I start. Yes.
The equation you just showed that you're about to work out, those aren't going to be on our test because that's what we did today, correct?
The questions that are on the practice test are not going to be on the test, but there will be a difficult balancing equation just like this one on it. It won't be this one, but it'll be like this one. Okay. And that's the same thing for everything. Now, there is a 28th question. 28, 29, and 30. There are 3 questions on this that are not disclosed. And they're sort of like the one that we had on the quiz. Remember on the quiz, there was one question that came from very early on in our very first day about the corpuscular nature of everything, mass, distance, space, distance, and time. And I didn't include it, but electrical charge is the same way. It's particulate. You saw that when you did the Millikan oil drop experiment, or you're doing that today, or starting it today. Okay, all right. Now let's look at this, and then I'll give you the links and the discussion on the lab. 27, and it's C2H6S plus N2O5 goes to CO2 H2O N2O and SO2. All right. Okay. All right. Now, what we do first, we're looking for elements to start with. Carbon is in just one place on the left and the right, so I'm going to put a dot on it. Hydrogen is in this compound and this one only, so I'll put a dot on it. It's a possibility. Sulfur, is in this one and this one. It would be okay start. Nitrogen is in this one. I guess the only one I eliminate on first pass is oxygen. Oxygen is in every one of the formulas on the right, so I surely can't start with it. But I can start with any of these other 2. My rule is I'm going to start with hydrogen because it's the biggest number. Okay, so a 6 and a 2. All right, so to balance hydrogen, I'll need a 1A here, and I'm going to need a 3A here. That gives me 6 hydrogens on 6A hydrogens on each side. I need to re-emphasize my dots on carbon and sulfur and on oxygen. So now I'm looking at these elements. I can do any one of them that I want to next. So I guess I'm just going to pick the first one. I'm going to do carbon next. There's 2A here. I need a 2A here. Dot and balance. Okay, now I've got sulfur. Sulfur, I've got 1A on the left and 1A on the right. And sulfur is balanced. That make sure I can read my own writing, okay? All right, so now sulfur is balanced. The next element that I should try to balance would be oxygen. That's the ones in the elements that have been dotted. Oxygen. I can't do oxygen because it's in one formula here and one formula on the other side. So I have to do nitrogen, but nitrogen is not in the A group. I can't balance nitrogen by putting some number of A's here. So that means I've got to switch to the other variable B. So I'm going to put a B here to balance the nitrogen and dot the oxygen. Now, if you look at this, I've got a coefficient here, I've got a coefficient here, one here, one here, one here, and one here. So everything has a coefficient, everything must balance. The only one I have not balanced is oxygen. So I'm going to make oxygen balance. And on the reactant side, how many oxygens? I've got 5B. Now, on the product side, how many oxygens I've got? 2 times 2A is 4A. I've got oxygen in this one. 1 times 3A is 3A. I've got oxygen in this one is a B. And I've got oxygen in the last one, and that's a 2A. So 5B equals 4 and 3 is 7, 9A plus B. I can subtract a B from both sides. I get 4B equals 9A. So A is equal to 4 and B is equal to 9. So if A is 4, this coefficient is a 4. B is a 9, this one is a 9. This A is 4, 4 times 2 would be 8. This is an A, 8. 3A, 3 times 4, this is a 12. B is a 9, that's a 9. And A is a 4, that's 4. So the coefficients are 4, 9, 8, 12, 9, 9. Okay, what was the answer? It says A is correct. Let's see the number of oxygens. So for the number of oxygens on the left, I have 5 times 9 would be 35. Uh-oh. 45. My brain, I have brain freeze here. 5 times 9 is 45. Okay, so that satisfies the first part. And let's see how many I've got on the other side just to see that right. 2 times 8 would be 16. And 12. And 9. And 18. Let's see. 9, 8 and 2 are 10, 19, 25. Carry the 2, 2 and 3 is 4. So A is the correct answer. So that is the balance. Okay. Are we all good?
Could you move your paper up so we could see the bottom of what you did?
Oh, sure. Sorry.
Thank you.
Oops. Where'd it go? Somebody's mic's open. There we go. Okay. That I was checking down here to see that response A was correct, 45 oxygens on each side. So for the oxygen balance, I did it right there. So 5 times B value is 9, so that's 45. And then I had 2 times 8 is 16 oxygens from the carbon dioxide. I had 12 from the water, had 9 from the N2O, dinitrogen monoxide, and 2 times 9, 18 for the SO2, sulfur dioxide. Add them all up, I got 45 equal 45. So that is the correct balance. Okay. Any other questions about the practice exam or anything? It will become visible later on today or early in the morning to you on D2L. The exam will open at class time, 7:30, and it will terminate 55 minutes later. And once we finish that up, I'll send you a link to Zoom as well, so you can come over to Zoom and we'll get ready to do our lab for that day and our second hour of the lecture and our lab for that day. All right, so I want to remember to turn the recording back on when we came back to work that second set of problems after our break. But that was just reviewing the quiz. All of the material that's going to be recorded onto YouTube, and then you'll get the link later, will be all of the class material, but it won't have all of what we did on the practice exam on the recording. Okay. All righty. Let's take a little bit of a break here, maybe another 5 or 10 minutes. Let's convene at 5 minutes until 11. So I'll change my note here to back at 10:55. And I'll discuss the lab with you and tell you a little bit more about where I am with the grading and what my plans are for that. I have not graded the lab that you put in the Dropbox for experiment 2, and I'll get to work on that and the rest of the grading. If you've sent things into the Dropbox that's been graded, I have attached a file to it that explains the grading and the grade. So you will have those grades, graded checkpoints available to you. I'm not sure how I'm going to handle the ones that weren't done in Dropbox. I will be able to give you the grade. It's hard to, and I would have to send each person individually a file with the worked out solutions on it, and that gets to be a problem. I had a program on campus on my office computer. It was called KU Tools, and it allowed me to do just exactly that. I could say, okay, I want to send the class the grades they got for checkpoint 1, number 1. And I just push a button and poof, there they go. And each one gets only his grade. I don't have that program on my computer at home, so I can't do it that way. And it takes an awful lot of time to do it by individual emails with individual attachments. So what I'll probably do is once I get all the checkpoints graded, I'll upload the grade. It'll be a composite grade of all of them. And you will know what you got on the ones that's on Dropbox. So you can figure out, I guess, how many points you missed on the other ones. And if you've got questions individually that, hey, I didn't really know how to do checkpoint 1, number 3, and I think I missed points on that, I will be able to answer it with you individually. So I'd rather handle them individually for people that can't figure out what the checkpoint grade actually means and which ones you actually missed of those first 3. But the others, beginning with checkpoint 2, number 1, there are or will be Dropbox links for each one of those. And once I grade those, I will publish them with the grade file attached to it. Okay, all right. Let's take a couple minute breaks.